Welcome back to the Igniting Research Passion series, where today, in Volume 6, we will be talking about the topic Transforming Computer Vision with Transformers. It's undeniable that our future footsteps will lie in the path of AI, and vision transformers will play a significant role in that journey. So, let's learn all about it from our renowned speaker, Dr. Sachith Seneviratne, who is a research fellow at the University of Melbourne, Australia, whose studies focuses on AI. He has 10 years of experience in generative and discriminative AI, and his work mainly revolves around deep learning techniques and foundation models with an emphasis on scalability, modularity, and extensibility. Dr. Sachith's research interests include computer vision, natural language processing, and using large language models in modalities beyond vision and text. So, he's one of the perfect speakers to talk about the topic today. So, without further delay, we hand over the session to you, Doctor.
Yes, thank you for the very kind introduction. Let me just share my slides. All right, today I'll be talking about the topic of transforming computer vision with transformers. I'm a research fellow in computer vision at the University of Melbourne. And this is a very exciting topic, and I'm very grateful to the organizers for extending an invitation to me to speak with all of you. If you have any questions at all, please pop them in the chat, and maybe one of the organizers can just let me know if there are any questions, and I can try to address them. And we can turn this more into a discussion as we go on, and I'm happy to take questions live. So if there's anything that's unclear or you'd like to get more details on, I'm happy to facilitate that as well. Right, so I thought before we begin that it would be good to take a step back and have a look at what exactly AI is. And where we are in terms of the field of AI. So AI is the area that is interested in imbuing reasoning skills into computational systems. So specifically, the ability to learn from experience is very powerful in the context of computational systems, because obviously computational systems tend to do the same things over and over again. So even in, for example, computer science, when you write an algorithm, whether be it deterministic or more stochastic in nature, it tends to perform the same task over and over again, perhaps with varying inputs. So the ability to learn in this regard is very powerful, because it's essentially what sets humans apart from most other animals that are around us. It's our capacity to learn from our experiences that gives us a competitive advantage in natural selection and so on and so forth. So naturally, embedding some of these reasoning skills into computational systems would undoubtedly give them considerably more capacity, and would in turn allow them to deliver more human-facing functionality, because humans expect each other to adapt through interaction. So the ultimate goal of the field of AI is to enable that kind of growth within the computational systems. And you'll probably see some of this to some extent in your day-to-day capacity nowadays. Like, for example, if you are on social media, depending on your behavior, the content that you see will be kind of curated towards that. So that's all AI working under the hood of those systems to deliver curated content that perhaps better matches your interests. But at its core, the field of AI also tries to mimic the human senses and capabilities, and this is largely where reasoning about vision and language come about, which is especially topical today because transformers are seeing a lot of use in these two modalities in particular, but we'll have a look later on into how it can be extended beyond these domains as well. Now, in this regard, it's really interesting that core research focuses so much on the human senses, but that is again to facilitate further automation in many different fields. For example, in vision, that's readily seen in sort of industrial automation applications or even robotics and advanced applications like self-driving cars and so on and so forth. So it deals with the human sense of perception. So, for example, if you wanted to differentiate between a ripe fruit and an unripe fruit, we as humans develop sort of heuristics, or we develop a process of learning and reasoning about our knowledge of the world through our perception that allows us to do that. And the same with language. Language is one of the skills that we learn very early on. And there's this thing in learning languages as well, where after you learn a few languages, learning more languages becomes even easier. So a lot of these skills we take for granted as humans because we are biologically programmed to develop those skills. So the field of AI is interested in embedding these functionalities onto computational systems as well. Now, in terms of progress in AI, there's been a sort of an explosion of progress in the last 5 to 10 years, and that this is largely driven by the emergence of the deep learning archetype. And really the modularity of the learned knowledge within that context. And now what I mean by this is it's the same sort of concept you'd see in computer science or software engineering, where if you build a modular system or a modular library or a module, for lack of a better word there, you can kind of reuse it across different applications. So if you have a sort of a function that can let you perform multiplication, then you don't have to go back and implement that again for usage in different setups. So while this gives you additional benefits like encapsulation and so on, the key benefit of modularity is that each piece of functionality is only created once and can be used multiple times afterwards, potentially infinitely many times, as long as that is useful. So this same abstraction that you see within sort of more functional design or modular design in computer science or software engineering can be applied to deep learning, but at a sort of a higher level or a higher tier of applicability. And that comes from the fact that the knowledge that is learned by AI models within the deep learning context can actually be pipelined into other models. So if we were to take an example of that in our day-to-day lives, it's really difficult to come up with something like that, simply because of the fact that humans are sort of not capable of communicating very effectively with each other, right? Because if you think of the process of communication, we form like an internal picture or an internal monologue of what we want to transfer to someone else, and then that gets decoded into language, which then perhaps gets decoded into audio, which gets transmitted to someone else. It goes to their ears, so they hear what we are saying, and then that again gets sort of encoded into language, which then someone uses for reasoning. So there's a few layers of separation between what we wish to communicate and what is actually heard by the other person on the other side of the conversation. Whereas with AI systems, because of the innate neural representations, we can actually just sort of pipeline them together. So the human equivalent would be something like joining people's brains together and getting them to talk together, which sounds very something you'd see in science fiction or so on. But in practicality, what this means is that if an AI model gains sufficient knowledge, then it can transfer a lot of that knowledge into other AI systems. So this becomes really powerful, especially across different modalities, because if there are different models or different deep learning systems that are better at different modalities, then they can be made to talk to each other. and that will let them sort of develop even better functionality in working across the different modalities. So what I mean by modalities here is things like vision, text, or audios. You can essentially think of them as a mapping between certain types of data. And the benefit of reasoning about data in different modalities is, for one thing, it lets us organize our data better. But in terms of AI, what it really lets us do is develop capabilities within those modalities and then combine them into applications that are at the multimodal level. So this is really where AI is headed at the moment. It's really towards those multimodal systems. You may have seen some of this in some of the chatbots or the language models that are very popular. Increasingly, they are able to ingest images or even create images, and we'll have a look at some of those applications and some of those things in the later slides. But really, this trend towards multimodality, or this trend towards being able to handle lots of different types of data, whether it be converting text to speech, or speech to text, or vision to text, or text to image, or speech to image, or whatever it is, we kind of need a central vehicle for reasoning about these modalities. And what I mean by that is like a deep learning architecture or a AI architecture that can be the central vehicle for reasoning about these modalities. And that's really what the transform architecture is. So the transform architecture is a really old architecture. It came about in about 2017, so it's been around for a very long time now. So again, this is sort of one of the things that's kind of unique in AI research is things become obsolete very quickly. So when I mean very old, even though it's been like 7 years, things have changed monumentally in those 7 years. So it's a field that develops very rapidly. But at the same time, that means it's really exciting because there's never a dull moment if you pay attention to what's going on in the field. In fact, it's very difficult to pay attention to everything that's going on in the field. But even if you pay attention to the things that are of immediate interest to you, you'll find it very fulfilling in the sense that there's always something to do. There's a new toy to play around with. You can combine them in interesting ways and so on and so forth. But at its core, the transform architecture is a sequence-to-sequence modeling tool that uses the attention mechanism. Now, we won't dive into a deep technical discussion of the transformers architecture because there's plenty of videos and other content that you can refer to for that. But what I'll try to do is I'll provide intuitions as to how you can use these architectures and provide ways in which you can leverage them effectively for specific use cases. And we will try to see how it can be generalized at a higher level to abstract out the key details that will let you use it in different ways. We'll also have a look at how these models are trained, potentially some of the specific training techniques and the intuition behind them. So one of the main issues with transformers architectures is that they tend to require a significant amount of data. But at the same time, once provided with that data and the necessary compute to ingest that data, they actually tend to perform fairly robustly across different modalities. So how can we get around this issue of data hunger? And really, when we talk about data here, typically AI systems require what we call labeled data. So the concept of labeling is also innate in human learning. For example, when we are very small, our parents may sit us down and point to an apple, point to a picture storybook of the alphabet and point to the letter A and say, A is for apple and so on and so forth. So that is an example of labeling or sort of training based on labels. So the letter A here is the label, and if it is being pointed to by someone, then there is a process of teaching that is happening there. So in essence, the letter, we form a neural connection between the letter A and perhaps the shape of the letter A, the sound of the letter A, and its contextual use in language. So the same process needs to happen with AI as well. The only issue is that, for example, this is what the example I used is just one instance of teaching. And it is a very basic example. So if you want AI systems to do very complex things, it will require more and more data. And the issue with that is labeled data is generated by humans. So in any AI system, the main issue with scalability tends to revolve around the human aspect of the project. So, for example, if the ImageNet project, which was, I think it was in around 2012, labeled 1.3 million images, and is one of the gold standard data sets even up to this day. So they were labeled based on the content within the images. But the issue with having humans do the labeling is even the labeling process is imprecise because well, humans make mistakes the same as AI systems. So in other words, a lot of the techniques around the use of transformers is trying to remove the human labeling issue out of the loop to some extent. So there's a lot of interest in leveraging unlabeled forms of learning. So that's where self-supervision and contrastive learning come in. If you're interested in these topics, please do read a bit further. I'll provide some intuitions around that. So I think there was a question in the chat. I'm happy to take the question. Yeah, okay, all right, I'll continue then. So where was I? Yes, so self-supervision and contrastive learning. So I'll touch briefly on self-supervision so that you can get a sense for how these systems work. But in essence, the main thing to remember is wherever possible, we want to leverage unlabeled data flows. That's not always possible because the issue with unlabeled data is typically it's unstructured. So for example, when we are babies, when we are less than 1 year old, very often our neural circuits are not developed to the level of being able to handle labeled data. So we deal with the world in a sort of an unstructured way. And this is the same for many animals as well. So there is a process of getting to know the world without necessarily knowing what things are. So you, as a baby, you'll play around with whatever toys are in the crib. You'll look around. You'll listen to your parents or dogs barking or so on and so forth. So these are all forms of learning, and they help in the human development process. They help develop the initial structure or the initial model of the world that we rely on for later use cases. So this is sort of the same intuition that is used in this kind of unsupervised learning in this case. And unsupervised here means just the fact that the data does not have labels. And we'll see an example of what I mean by self-supervision later on. But it's essentially a form of teaching yourself what is required, but in an unlabeled way. Right, so these are some of the key tools that we have in the transformers phase. But where exactly is AI headed? So right now there's a lot of interest in multimodal systems. Yeah, so this is exactly why we need the transformers architectures, because it allows us to embed these these different modalities within the same vehicle. And that includes vision, text, and audio. Now, the interesting thing about the text modality is, so for example, this paper that I've mentioned over here, Vaswani et al. 2017, the initial, which proposed the transformers architecture. It started in text, and there's a really good reason for that, because text lends itself very well to sequence modeling. So sequence modeling is essentially sort of turning the data into a single sequence and trying to regenerate it again using some sort of learning mechanism. So this is a very common technique that's used in AI, and the key intuition behind that generation is that if you have a piece of data, regenerating it can be a very strong objective because it indicates that the model has learned everything there is to learn about that specific piece of data. So for example, if it's a sentence, if you mask out part of the sentence, which is sort of like you're playing hangman with the sentence, right? So you remove some of the words in the sentence and ask the AI model to fill it in various ways, that can be a very powerful objective. In the same way, in a vision system, you can mask out part of what the image contains, and that can allow the model to learn what is required to fill in the blanks, right? So you'll see that, like, if you sort of listen to me explaining this, you might think back to like some of the exercises you have in school or even university, for example, right? You will have examples where there is a sentence that has been given to you and there will be a blank that you need to fill in. So the blank that you fill in, if it's at the exam, will perhaps have required you to gain a significant amount of knowledge about the subject to fill that blank in. So even though it's a very simple objective, in the sense that, okay, fill in the blank, that seems very straightforward. Contextually, filling that blank with the correct answer can be a very difficult task. So the other main thing about that specific task is that task can be generated automatically. So for example, all that you need to generate such an objective is any piece of data and the ability to mask or remove part of that data. So if it's an image, you remove like a small block somewhere in the middle. If it's a sentence, you remove a word somewhere. If it's a piece of speech, you remove like a certain block. If it's a time series, you remove perhaps a contiguous period, and so on and so forth, right? So this ability to generate the task without human intervention allows the data to be scaled almost infinitely, right? So whatever amount of data you can have, you can create a lot of tasks with that amount of data, and you can set these models to learn on that. So this is the intuition behind self-supervised learning, and it's a very powerful objective. Right, so let's have an example of what that exactly looks like. So we have over here the concept of pretext tasks, and that simply means that it's a task that can be created without human intervention, right? So it can be automatically generated from the data by sort of a simple program, perhaps deterministic, perhaps stochastic, that you can set up without too much trouble. So the interesting thing about that is that so for example, in the images here, one of the example on the left is using jigsaw puzzle solving. So for example, in this car, if you take this middle bigger block and you break up the image into 9 parts, like you see over here, and you shuffle them and get a neural network to align them in the correct order, then that becomes a very powerful objective, because the model must learn not only the correct position, but the relative position with respect to each other, right? So by providing it with this kind of task, so there are 2 key points here. The first one is that it can be generated automatically. So you can take any image like this, you can randomly pick a block like this of a specific size, and you can turn it into blocks and then shuffle them and get the neural network to solve this problem. This allows the model also to learn about the spatial relationship between the parts over here, right? The same way over here, the model is required to predict the relative position with respect to a query image. So here in the middle, it's provided the nose of the cat. So the model should learn over time that the ears of the cat are generally going to be above the nose of the cat. And based on the contextual information, for example, the shape of the ear is like this in this image, so that should indicate to the model that the position is to the left rather than to the right, right? So the model needs to reason contextually about these things. And that is sort of what allows the models to build up some of these. So you can see based on the timing here that some of these ideas actually predate the transformers architecture. It just and this is the beauty of research, right? Sometimes these tools are, some of these solutions are proposed even before the right architectures to ingest them are introduced, and then you have these two different pieces of the puzzle, and third party puts them together, and it leads to powerful breakthroughs. On the image side, there are a lot of different techniques that have been proposed. A couple of the better ones are Moco and Dino here. If you're interested in this area, I suggest you go and do a bit of reading. There are some really interesting works out there. I'll refer to one of them later on in one of the applications I'll be talking about as well. Right. So in terms of applications, first we'll have a look at the area of design. I thought this would be a really interesting one because it's a bit out beyond what we'd normally expect, because typically when we do sort of AI, the applications are very often in engineering, in medicine, and more objective fields, whereas design is a bit more subjective in the sense that what is pleasing to one person may not be pleasing to someone else, and that makes it very interesting to explore using AI. So again, it's difficult to quantify at scale, but then AI systems are all about quantifying things at scale. So it leads to interesting dynamics sometimes. Additionally, there's considerable potential for generative AI workflows because design by its nature is typically generative. So that means there's a lot of disruption potential. And to be honest, it's just a lot of fun. You can look at very interesting images, you can generate nice videos, you can generate sound, you can generate graphs, and so on and so forth, right? So how can AI help? Well, you have generative approaches, which means the AI system generates something of interest. And then discriminative systems are the flip side, where the AI system will look at something and provide a decision of sorts. So for example, it might look at this image over here and decide what kind of car it is. Or it might look at this picture over here and say that the image is one of a cat. So it's making some kind of decision, and that's powerful in sort of automated workflows for various use cases, right? Right. So as far as generative approaches are concerned, at least on the vision side, diffusion is a very recent sort of phenomenon in this area. And the main intuition behind diffusion is it's really the same thing you've heard of in physics class, right? Back in high school or so on. So if you kind of randomly allow the gaseous particles in a room to move around, their position will sort of shuffle about randomly, and it's difficult to sort of figure out the location of any given particle. So the diffusion process in AI is somewhat similar. It's sort of based on the fact that if you take a piece of information, for example, this image of a person's face, and you add noise to the image in a very controlled manner, over time you will end up with completely random noise, right? So that's the main basis around diffusion. Now you might ask, okay, why do we care about this? So this is the forward process of the diffusion process. But what about the backwards process, right? So some very clever people have gone ahead and modeled the backwards process. And that is really leading to a lot of what you see in terms of visual generation from the AI on the AI side these days. And a lot really it's building on this fundamental very interesting piece of work that I think started around 2012 or 2015 or so, around the mathematical process they call diffusion. So for example, in this image, you go completely noise, but then if you can map the backward process, at some stage, you can train a model if it's been trained on enough faces, for example, it can use the noise and go back and generate a human face or something like that. Not that you'd want to specifically generate human faces, but there are lots of obvious use cases for generating images, the main of which is obviously design, but then beyond that, it can be progressed further into generating videos and things like that, which lends itself to animation and so on. So it's very interesting what you can do with this. Now you might ask, why am I talking about diffusion in a talk about transformers? Well, the interesting thing is that you can actually, if you think back to what I said about pipelining AI models before, pipelining AI models together, specifically deep learning models, well, you can do that with diffusion-trained deep learning models and transformer-trained diffusion models as well. And that's what leads to a lot of the models that you're seeing nowadays around text-to-image generation. So this is an image that I generated from Dolly about 2 years ago, which is somewhat a decent amount of time ago, for one of my papers around text-to-image generation. So as you can see, this is generated from the simple text input for a painting of a public open space, which is ideal for walking, right? So the interesting thing about this kind of prompt is that it isn't specifically querying for anything objective within the image. So for example, over here, you can see the footpath is quite wide. Now, if you do any form of walking or cycling, you will know that you prefer to have a bit of space so that you can walk and cycle safely, right? And there are some very nice trees. It's very green. It overall looks pleasant, right? And a lot of this is without specifically prompting for that, but is implicit in this bit over here, the ideal for walking bit, right? So the AI model has interpreted it in a specific way and generated this image. So the architecture for these models are increasingly based on transformers in the first half, which is the text part. So the understanding the text is done through aligning text and images together using transformer architectures and contrastive learning. The end part, or the latter half of the generation process, is run by diffusion models. So it takes the text input, converts it into a format that can be understood by vision models, and then it generates the vision output using the diffusion process. So if you are interested in this kind of work, I highly recommend the stable diffusion paper, which was released around 2022 again, in CVPR, I think. So you can have a look at that one. Yes. So why do we care about this sort of thing? Well, obviously we want to take models like this and use them to generate things, that images that we like, right? For example, images of cats. So that's a picture of my cat on the left, Zoe. So what I've generated in the rest of the images are actually other vision outputs for the same image. So in the next few slides, what I'll try to do is to show how we can impose additional conditioning on the generation process. So conditioning in this context means we bias the model towards generating things that we want to generate, right? So what I've done here is I've taken an edge, generated edge detection, run edge detection algorithms to create edge maps. That's what you see in the second and the fourth image. The third image contains what we call a segmentation map. So a segmentation map is essentially converting the original image into semantic context. So I imagine the red part here is like cat or something like that. So it assigns labels to this space and provides a bit of context that we can use in the generation process again, right? Now, the interesting thing here is, again, these are AI models. The edge detection and so on and so forth are also AI models. So we can use an image, generate outputs using AI models, and feed them into other AI models to generate interesting images. So I'll show you how I've used these to generate specific outputs in this case. Not very specific, but you can sort of see how you can bias them towards a specific outcome. So by inputting the by inputting only a text condition. So again, this is similar to this one. So if you just indicate a text input similar to this, saying a cat or something like that, it it will simply generate an image of a single cat without any specific features that we desire. However, if we incorporate additional conditioning, we can get a bit more of a control generation. So this is using the segmentation output over here. And now you can see the position of the cat has changed to better mimic the original input image, right? So that indicates more control, but again, the background is a bit random. There's a crayon here, so that's potentially not what we want. But the powerful thing here is we can overlay different kinds of conditioning. So for example, this is overlaying all three types of conditioning with a lower weight and under the same setting. And now it starts to preserve more of the original image that we used to generate the conditioning. If we take this one step further, you can see that it bears a fair bit of resemblance to the original image. So if you go back to the original one, you can see there's like some background, there's a building in the background, and so on and so forth. So you see here that it maintains some of the structure, but perhaps not all the semantic information, right? So perhaps there's space for improvement in this case. But really what's powerful here is that you could generate any kind of image that you wanted to, if you had the right kind of conditioning. And this is all using pre-trained models. So there isn't a lot of computational power that needs to go into these systems to do this kind of thing. Right, and here's an example from a research paper. I think this is from 2023 or 2022, that's showing similar things. Now here in the input image, you can kind of condition the image based on both text and image. So the green indicates here that the generation corresponds to this piece of text, and the light blue corresponds to this piece of text, and this is the result image that is generated, right? So you can see how systems like this might be very powerful, especially in the case of multimodal systems, because again, this is language over here, so it's language guided. So something like this could form a very powerful tool for a model that is proficient at language. So for example, large language models are increasingly being used with tools like this. So the large language model will take a task from a human and understand it, because the large language model is good at language. And large language models are like your ChatGPT and so on and so forth. So they have a good grasp of language and can understand potentially what the person communicating with them wants. It can convert it into a task, and then that task can be handed over to a different potential model, potentially handed over to a different specialized model that can generate an output and return it to the language model, which can then return it to the humans, right? So these are very exciting times for that sort of research, because that it allows this. It's almost interactive in the sense that the different models are talking to each other. Of course, I'm kind of abstracting out a lot of the underlying details here. But at the same time, if you pipeline enough of these things together, you can do some very interesting things, right? So the same here, this image, for example, is very somewhat complex, and you can actually make them arbitrarily complex. But obviously performance tends to drop off the more you complicate them, but nonetheless, it's still useful in specific use cases. So here's another use case in design. So this is from a master's student project at the University of Melbourne. It's generating floor plans based on very simple image conditioning, but somewhat complex text conditioning. So on the left, you can see the outer structure of the house, and then a detailed text prompt. It provides insight into what kind of details should be generated, and then there's corresponding ground truth. Now, obviously, you can't specify a house exactly using text like this, right? But the interesting thing is that the model picks up on this kind of ambiguity and can generate relatively similar outputs, but not always correct, right? Nonetheless, these generation capacities, this generation capacity is really interesting because it lets us develop more tools in this space and potentially iterate until um, uh, a usable result is generated. Now, obviously the important thing here is that a, any single generation does not need to be, every single generation does not need to be correct for there to be value in the generation. For example, if we go back to this, perhaps this specific image is not very useful, but if I were to generate 1,000 of these images or 1,000,000 of these images, perhaps I will get some that are useful. And that is powerful because, again, it's an AI system running this. It's very cheap. As long as you have the right resources and it can keep running in the background, it can generate a near infinite amount of samples, and then you can filter through those samples either manually or using another specialized system and come up with a few usable images or generations or videos or sounds or songs or so on and so forth, right? So this is really what is driving some of the excitement in this area. Right, so on to discriminative approaches. Now, again, here on the design side, in planning and so on and so forth, urban form and infrastructure are kind of difficult to quantify at scale. However, things like aerial images can provide a very concise image of a concise summary of what is going on in a specific area, right? So in particular, in large countries like Australia, this is a key issue because it's very difficult to monitor what is going on in all the different areas. And I'm talking more about development projects, infrastructure layouts, and things like that. It becomes very difficult to capture all of these. So the interesting thing about AI systems is they can actually capture a lot of this very quickly. So for example, with the improvements in satellite imagery and things like that, you can get a very large set of data images that can cover a huge area, like 100 million images, that can actually be processed by vision transformer systems because it's slow to train, but running inference is actually quite fast. And of course, the benefit is that it can be extended to any kind of sort of urban feature that can be seen from above. So this is a funded project that I've had for a while now. It's kind of wrapping up, but the interesting thing here is you can specify it to identify specialized types of infrastructure. And because the images are captured over a longer time, it's possible to look back in time to capture when certain things were introduced. So in this case, this is looking at cycling infrastructure in Melbourne and when it was introduced. So I'll let you have a look at this for a couple of minutes while I drink some water. Yes, and as you can see, it provides a very interesting, a lot of interesting insights into a given area, and this is very powerful even for policymakers, right? So, for example, if someone wanted to make sure that cycling was safe across from one side of Melbourne to the other, they could use something like this to identify holes in the infrastructure and use that to plan where to incorporate cycling infrastructure and so on. And the same idea applies to footpaths as well. So this is built on one of the vision transform approaches that I mentioned before. A lot of these papers are available on my Google Scholar. So if you are interested, have a look at my profile and you'll be able to see the papers over there. And this is the same idea we extended to footpath analysis, so pavements. And you can see the middle column is the actual ground truth, and the right hand side image is the generated output. So it's fairly robust. The top one is the original GIS layer captured by a council here in Australia. And the bottom one is actually generated using images by the computer vision segmentation system. So as you can see, it's fairly robust and it can generate these insights at scale and very quickly. Um, and the interesting thing about these generations is that they are both relying on the same overall vision transform architecture. It's building on self-supervision. So the self-supervision allows the model to build an initial representation of remote sensing imagery. And then it is specialized using the segmentation task to generate specific outputs. So segmentation is kind of generating pixel level outputs like this one. So as you can see, it's fairly robust and it's generating interesting insights. And it can do so at scale and in a robust fashion as well. So that's sort of really most of the material I wanted to cover in today's talk. And I'm happy to open the floor for discussion or questions at this stage.
So there's a question raised during the registration as how does the performance of vision transformers compare to CNNs on standard image datasets?
Yes, that's a very good question. Recently, vision transformers are seeing better results. Um, it's really a difficult question to answer because standard datasets cover a lot of different areas within computer vision. But if we talk about many of those, vision transformers are generating more robust results. Now, at the same time, if so there are two specific cases here, right? It really depends on computational capacity as well. So if there's a lot of computational resources, typically vision transformers will tend to be better. But there are some use cases where CNNs are better, and that's specifically in kind of low resource use cases. I think even in edge kind of use cases. So that's when you deploy things on edge devices and so on. In those situations, the CNNs can be better. There's actually another question that has been. Oh, okay, I think I see. It's been sent to the general chat as well. Yes, yes. But I hope that answers the question. Okay, I think I'm getting some direct questions. Maybe I'll quickly go through them. Yes, I think are there specific areas within computer vision where transformers are particularly advantageous to explore other than generating images? So again, for generating images, it's actually a different kind of architecture that's used. It's diffusion here. So I kind of explained that previously, but transformers can be used for generating as well, but typically it's for classification and discrimination that you use transformers. At the same time, it's a very powerful general architecture nowadays, but sometimes requires more computational power. So a very interesting angle to look at is transfer learning. So the interesting thing about transformers is that there are companies with a lot of computational capacity, like for example Meta, which is Facebook's new iteration, and so on and so forth, that train very powerful transformers and release them open source and open weight for anyone to use. So if you're looking for example, projects to look at and so on, that can be quite beneficial to take some of those powerful models and adapt them to your specific use cases. So rather than training a big AI system from scratch, you can actually use those powerful systems to your benefit. And that's a very good way of, especially if you don't have access to a lot of computational capacity, that can be a very good way to get good results very quickly. In terms of self-supervised learning, the embedding space is of specific interest because it can let you capture the meaning of an image in a quantitative form, and that can lend itself very well to specialized use cases. So if you have a look at my Google Scholar, you'll see a few papers where I've done that. One of them was looking at cybersecurity using vision transformers. But the same idea can be extended to many other areas. You just take kind of a pre-trained vision transformer, and all you need to train is a very small additional neural network that can let you do more specialized tasks quickly. There's another final question, I think, saying, spoke about, that's the question, can scroll up. You spoke about text-to-image generation in Copilot image generation as well as in ChatGPT generation. We face challenges like if we ask to reduce the objects or make it less crowded, it makes it more crowded. Yes. So how can transformers be used better? Yes. So that's a really good question. This is one of the issues with certain closed models. For example, ChatGPT is a closed source model in the sense that it's closed weight, so we can't see the weights or we can't peruse the weights ourselves. So it's up in the cloud. So it's very difficult to identify what's causing certain issues, right? So we have to kind of speculate when that's the regard. But for example, systems like Llama, Meta's Llama model, and so on and so forth, are actually openly available. So if you want to build on top of systems like that, then that can help us identify what's wrong with some of these models and see what we can do. So, but there are definitely generation level issues with some of the models. It really depends on what additional model it's using for the image generation process. So these are all open research areas, but things move very quickly in these areas as well. So sometimes it's very difficult to get a good sense of whether the problem has been solved or not. But if you're interested in these sort of things, I recommend you look up top conferences like ICCV or CVPR. You will find some really, really interesting work. It's a good exercise to learn how to just engage with those papers and learn how to read them and see how you can use some of the artifacts that they've released as well. Because a lot of research in this area is actually open source. It's readily accessible, it's reproducible. So the barrier to entry into vision research has never been lower. And it keeps getting lower as more and more research projects are open sourced. So it's a really good time to be interested in this area.
Thank you, sir. Kavi, you can continue.
Good evening. On behalf of the IEEE Women in Engineering Student Branch Affinity Group of the University of Jaffna, I would like to express our heartfelt gratitude to our esteemed speaker, Dr. Sachith Seneviratne, for sharing his insights with us. Dear sir, your comprehensive overview of how these innovative models are transforming the landscape of image recognition and analysis has undoubtedly enlightened us all and provided invaluable knowledge that will benefit on our academic and research pursuits. We deeply appreciate the time, effort, and expertise you generously shared with us. Sir, please accept the virtual token of appreciation we have prepared as a small gesture of our gratitude. I would also like to extend a warm thank you to all the participants who took the time to join us tonight. As we come to an end of today's session, it's perfectly okay if you are unable to switch on the cameras, but we request everyone to join us for a group photo. It would be wonderful to capture this moment together. Thank you once again and have a wonderful evening.